Guys, we're going to talk about modes of shear failure today. Now this is the diagram when a concentrated load is applied, the SFT and that is the shear force diagram and the bending moment diagram. For a beam subjected to concentrated load, the ratio of bending moment and shear force at the initial section subjected to maximum shear force is expressed by a distance called AV. In the diagram is shown AV, which is known as the shear span. The distance AV represents the domination of shear over flexure. Shear failure is a function of ratio of AV by D, where AV is shear span and D is the effective depth of the beam. This ratio, AV by D, provides a measure of relative magnitude of the flexural stress and shear stress, and hence it enables a prediction of mode of failure in the beam. With this magnitude, that is the ratio's magnitude, we can provide a measure for the flexural stress as well as the shear stress, and hence we can figure out what type of failure that occurs in the beam. And depending upon the value of AV by D ratio, a beam may experience about 4 cases of shear failure. Okay, in my previous video I mentioned about two stresses acting in when a transverse load acts on a beam, that it a flexural stress as well as shear stress takes place. Now the magnitude of flexural stress and shear stress influences these factors. Those are magnitude and direction of the maximum principal stresses, development and growth of internal cracks. If shear is more, the direction and magnitude of it will be the maximum principal stress. If flexural stress is more, the magnitude and direction of the will be the maximum principal stress's magnitude and direction will be indicated by flexural stress if flexural is more, and the other way around if it's shear stress. And also it also influences the development and growth of internal cracks. These stresses, for flexural stress and shear stress, they are proportional to each other, that is m by bd square and v by bd respectively, where m is the bending moment, v is the shear force at the beam under consideration, b is the width of the beam, and d is the affected accordingly by the flexural stress and shear stress ratio, that is fx by tau is equal to force on F1 into m by bd square by F2 into v by vd, which is equal to F3 into m by vd. That is the first equation, where F1, F2, F3 are proportionality constants. In such case, for a beam subjected to concentrated loads, the ratio m by v at the critical section is subjected to a maximum shear at the exact distance of the shear span, that is between the support and the load. In such a case, m by vd becomes equal to a by d, then therefore fx by tau will be proportional to a by d or av by d. That is the second equation. It can be seen that dimensionless ratio a by d or mv by d provides a measure of relative magnitudes of the mode of failure of the beam under combined flexure and shear. This prediction is based on considerable experimental evidence involving simply supported beams of rectangular cross sections subjected to symmetrical two-point loading. The previous figure I showed had two concentrated loads, and the beam has been subjected to symmetrical two-point loading. Okay. Now let's look into the 4 cases of failure that will take place depending upon the magnitudes of the ratio. Now when A by D is less than 1, in very deep beams, that is, if the ratio is less than 1, it is a very deep beam and it does not have any web reinforcements. In very deep beams, without web reinforcements, inclined cracking transforms into a tied arc. It sees this figure is the tied arc, the first one. It's in the form of an arc. The inclined cracking turns something like this into a tied arc, and the tied arc may fail due to various reasons, either by breakdown of its tension element, that is a tie, the longitude of its longitudinal reinforcement. It can be either by yielding, fracture, or failure of anchorage, or a breakdown of its compression core, that is known as the strut, that it happens due to the crushing of concrete, which was shown in the second figure um, in my previous slide. Now we look into case 2, that is when A by D ratio is less than 2.5. In relatively short beams with A by D in the range of 1 to 2.5, the failure is initiated by an inclined crack, usually a flexural shear crack, and it can take place either by crushing of the reduced concrete section above the tip of the crack under combined shear and compression, and it's known as shear compression failure because the combination of shear and compression crack takes place, or shear tension failure can take place, that is secondary cracking along the tension reinforcement, that is splitting cracks. And both these types of failure usually occur before the flexural strength of the beam is attained, that is the full moment resisting capacity is attained. However, when the loads and reactions applied on the top and bottom surface of the beam are so located as to induce a vertical compressive stress in concrete between the load and the reaction, the shear strength may be increased gradually. It increases gradually in the case of the A by D ratio being less than 2.5. It increases significantly, hence it requires heavy loads to cause inclined cracking. Now comes the third case, that is when the A by D ratio is greater than 2.5 but less than 6. Beams having ratios in more than 2.5 fail either in shear or in flexure. The limiting A by D ratio above which flexural failure is certain depends on the tension steel area. Also, the strength of concrete as well as steel. Generally, it is in the range of value 6, that is, it's less than 6. For beams with A by D ratios in the range 2.5 to 6, flexural tension cracks they develop earlier. Failure in shear occurs by the propagation of inclined flexural cracks. If shear or web reinforcement is not provided, the cracks extend rapidly to the top of the beam. The failure occurs suddenly and hence it is known as diagonal tension failure. See this diagonal? Since when the cracks travel to the top of the beam and it split into two, the failure occurs suddenly and hence it called diagonal tension failure. That means we have to add more reinforcement so as to increase the shear strength gradually, and it can be carried until failure occurs in a shear tension mode, that is yielding of the shear reinforcement, or in a shear compression mode or in flexural mode. Next is that's the last case, web crushing failure. Thin webbed members may fail due to crushing of concrete under diagonal compression forces such as I-beams with web reinforcements. And this crushing of concrete takes place in the web portion between the incline cracks under these diagonal compression forces. This is the picture of the failure that's taking place when the concentrated load is subjected. Inclined cracks appear on the thin web beams and usually happens in I-beams. So those are the four cases of modes of failure that we have to look into. I hope you understood the concept of how the ratio of bending moment and shear force has a significance in the flexural stress as well as the shear stress, which provides the magnitude and direction of the principal stress, maximum principal stress of the beam, and how these stresses can lead to four cases of crushing failure based on the ratio of AV by D, where AV is the shear span, that is the distance between the support and the load, and D is the effective depth of the beam. So that is all for today. Thank you.